Let's take a look at the concept of a limit in mathematics. The idea of a limit allows us to think about sort of the process of a function. If we have a continuous function, like x plus 2, we can vary the x value. And in particular, what this limit is saying, what this graphic is talking about, as the x value gets closer to 2, we're interested in thinking about what happens to the function value. So one way to describe this, and maybe kind of dig into it a little bit, is to represent a variety of x values. And let me start by writing down some x values that are less than 2, but are getting closer and closer to 2. And then if we think about the function values that correspond to this, f of x is x plus 2. So this becomes 3.9 and 3.99 and 3.999, which it's pretty obvious these are getting closer and closer to 4. But the idea of a limit is not interested in what's happening exactly at 2. We're really only interested in what's happening as we get closer and closer to 2. So on the other side, I could think about 2.1 and 2.01 and 2.001, values that are above 2. And again, we see, this would be 4.1. If x is 2.1, x plus 2 is 4.1, and 4.01 and 4.001. So our values, again, they're getting closer and closer to 4. And so we say the limit as x approaches 2 of x plus 2 is equal to 4. So now let's take a look at the definition of a limit. We're going to kind of look at a casual version of this. There's a more careful mathematical definition that you might come across someday, but for us, a casual definition is okay. We write this notation or this notation if the function f of x gets arbitrarily close to the single value L, the single real number L, when x gets closer and closer to c. So again, we're not really interested in what's happening exactly at c, but the process of getting closer and closer, of moving closer and closer. And this turns out to be a really important concept to think about for calculus. Now, this notation, if you have to read this notation, we would say this is read as the limit as x approaches c of f of x equals L, or is L. So in particular, this is the limit as x approaches c of f of x. In this other version, we would say f of x approaches L as x approaches c. Now let's look at an example. Our example is going to involve the absolute value function, which is described here using piecewise notation. For any x value that's less than 0, the value of the function is going to become its opposite. So the absolute value of -5 equals 5. But for any positive number, the absolute value of 17, for example, it just equals 17 again. We just get x back again. Sometimes absolute value is thought of as the distance from 0. Now our function f of x is defined using the absolute value. We're taking the absolute value of x divided by x. And for any negative number, what's going to happen is the absolute value turns the numerator into the opposite, but the denominator stays the same. So I get, for example, 5 divided by -5 equals -1. And we're always going to get -1 for any negative value. But for any positive value, like positive 17, the numerator and the denominator will be exactly equal to each other, so we get +1. And so we can represent this graphically. Our graph will be -1 for any negative value and +1 for any positive value. Of course, it's undefined at 0, because we can't divide by 0. And what does this mean for our limit? Well, this limit by default is a two-sided limit. So I need to think about both sides as I approach 0 from the right and as I approach 0 from the left. And because the two sides disagree, we say the limit does not exist. So the two-sided limit doesn't exist, but it's worthwhile to talk about, and in just a moment we'll look at the notation for when I want to talk about just the limit from the right side or just the limit from the left side. And those are called, shockingly, one-sided limits. So let's take a look at that idea now. All right, well, to describe a limit from the left, we just add a little negative sign next to the number. And to describe a limit just from the right, we add a little plus sign to show that we're interested in x values that are slightly larger than c. And then, in order for the two-sided limit to exist, the limit without a plus or minus, we need the left side limit and the right side limit to be equal. And then the two-sided limit has that same value. So it might be helpful to look at some graphical examples, and that's what we're going to do. I'm going to show this first one and then encourage you to pause and work on the others. So in this example, we start with -1 as our target value. And this is describing, approaching -1 from the left. So here's -1. I want to approach it from below -1. That's what this is describing. And as we approach the x value of -1, the function value seems to be reaching a height of 1. And from the right, as we approach -1, as we approach the x value -1 from the right, again, we're reaching a height of +1. Which means, of course, that the two-sided limit also equals +1. And because the function exists at -1, and we just have this kind of straight line to start with, the value of the function is also equal to 1 at -1. So using that same graph, there's sort of more interesting things happening at 1 and 2, and these other two sets of notation, these other two descriptions are talking about the limits and the function values there. So I encourage you to pause the video for a moment and try to answer those questions. Fill in those answers for yourself, and we'll share the answers in just a few seconds. All right, so let's take a look at these examples. At +1, we have a hole in the graph, we can see. As we approach that spot from the left, the value of the function is getting closer and closer to 3. The height of the function is getting closer and closer to the location of that open dot, which equals 3. As we approach from the right, the height of the function is also getting closer and closer to 3. And so the two-sided limit exists and equals 3. But the function value does not exist, and we usually say the function value is undefined, or you could also say, does not exist. So saying the function value is undefined is probably a little bit more descriptive, because what this is saying is that 1 is outside the domain of the function. The domain of the function does not include 1, so the value of the function is undefined at that point. But the limits are fine. The right limit, the left limit agree, and so the two-sided limit also exists. So now at 2, we have something a little bit different happening. So at 2, when we approach x equals 2 from the left, the value of the function is getting closer and closer to 2. And so the value of this limit is 2. As we approach from the right, the value of the function is getting closer and closer to 5. And so the two-sided limit does not exist. So undefined wouldn't really be the best way to describe it. We could say does not exist is better. Because they don't agree, we don't get a two-sided limit. But we do see there is a solid dot, and the height of that dot is 2, and so the function value is 2 at that point. In a lesson very soon, we'll work with limits more algebraically, but I think the concept of a limit, it's very helpful to think about these visual examples. I hope you enjoyed the video. Thanks for watching.